Well, despite the wonderfully appealing and simple geometry of the geometric expansion model and its explanation of some of the basic relationships of nature, it still suffered some fundamental problems. The cosmological redshift was not observable. The desired goal of an equivalency between matter and radiant energy was still missing, and time dilation was non-existent, at least as observed. And even the expansion of the universe itself would not be observable. The very foundation of the model is being eliminated. So now the solution to this issue was to expand the expansion. This is going to sound complicated, but it's proposed that our observable space is in motion and expanding within another unobserved space that is also expanding according to the same geometry that observable space is expanding. Now, this added some complexity, but it also resolved some fundamental properties, such as why the speed of light is the speed of light and the property of inertia. The ambiguous relationship associated with the energy of a photon over time became resolved. Also, there would now be a cosmological expansion of galaxies. Dark matter would no longer be necessary to explain the orbital velocity of galaxies, and dark energy would no longer be necessary to explain the cosmological location of galaxies once the effects of observable space and unobserved space were incorporated together. Now, there are 6 kinds of spatial relationships being imposed. And previously what was described as just the expansion of observable space. But let me go through some of the descriptions. You have a relative or local space. And relative space contains all observed measures of events and objects that are local, using local rulers and local clocks. Now, local is a relative term. Determining the relationship that establishes whether or not an observation is local is the temporal separation between the observer and the object, as defined by the time it takes for light to travel between the two, divided by the age of the universe. Now, the closer this ratio to 0, the more local the observations are within relative space. Since the age of universe is a very large number, we're almost all measurements in essence are locally. Now, you have now the other space is observable space, or expanding observable space more exactly. But I keep saying observable just because adding and expanding all the time just makes it a lot of extra words. Now, is formed by that. Now, this was described previously where we had this geometric expansion of space. And now we have an absolute space. And this absolute space is kind of referenced a few times in the past, but it's a reference frame that describes how our relative measures or how our observable space is expanding. It is from this reference frame that we are able to describe how absolute measures of distance and time are changing with the course of time. And then now we have unobservable space in motion along an unobserved dimension. And I will show some diagrams of that in a little bit. And then we have unified space. Now, unified space is where we add the relationships of observable space and unobserved space together, and as described by an eye of God perspective. And then we have unified local space, or local unified space, which is the relationships of observable space and unobserved space using local clocks and local rulers. And then when we measure events on a cosmological scale. Okay? So we have these, now illustrate these various relationships. Now, here we have, I'll go through the spaces we have here. We have relative space corresponds to region of space-time is locally seen and measured locally. So this is an expanding flatland universe, and we were sitting here, it'd be those measures we make really close to where we are now. Observable space records to the expanding flatland universe. So we go across and the distances are great enough, we would see that there's across here this expanding observable space. Now, unobserved space corresponds to the region described by the unobserved vertical dimension. So here we are moving along an unobserved dimension with an unobservable space. And then absolute space corresponds to the eye of God background that allows us to describe these things. And then unified space would integrate the integrated relationships of both this motion and the expansion together. And local unified would be using our local rulers rather than an absolute ruler. And I got some more diagrams over here kind of shows a volume of space, observable space within unobserved space, and where our observable space is in motion along an unobserved dimension. And then these are, well, some other diagrams that kind of illustrate it a little bit more detail. And then now, what about, let's talk a little bit about moving along an unobserved dimension. Some properties for motion through an unobserved space. Here we have what this would mean if here's our unobserved universe moving along an unobserved dimension. We can see that there would be an intrinsic velocity. Now, we wouldn't really see this velocity, but we would see this intrinsic velocity, and it all would be shared by everyone within this flatland universe. We wouldn't be directly perceive it, but there would be this motion along the unobserved dimension. And according to this model, since this velocity of observable space along an observed dimension is occurring within an expanding space, this velocity should also diminish over the course of time. Expansion comes at a kinematic cost. Now, this illustrates some of the properties I mentioned earlier about all these points A, B, and C would all share the same intrinsic velocity along an unobserved dimension. And then, now, this has an interesting characteristic. If all objects have this intrinsic unobserved velocity, what happens if they change direction? Okay, and here I have, there's an object, and we're moving along an unobserved dimension, and let's say we decide to go, we're going to go in this direction. Well, that means we have changed our we've changed our direction. And whenever there is a change in direction of motion, there is a resistance to that. And this resistance is the physical explanation for the property of inertia. Inertia is a result of our velocity along an unobserved dimension, and we notice its effect as soon as we move in any direction. Now, in a flatland universe, it's obvious to see, you know, if we go anywhere we go is going to induce this resistance to a change in direction. In a three-dimensional space, it's not quite as obvious, but the same effect would be. You'd have this intrinsic velocity. Any motion within three-dimensional space would incur a resistance to this change in direction, and we would experience this resistance, and we describe this resistance within our space as the property of inertia. So the property of inertia is being kinematically described. Why there is the property of inertia. Now, this next part of development has to do with the speed of light conjecture in E equals mc squared. Now, the question is how fast is the entire observable universe moving along in an unobserved dimension? Well, the mass moving along an unobserved dimension, a mass moving along the unobserved dimension with an unobserved velocity would also have an intrinsic kinetic energy. Okay, it had intrinsic velocity and an intrinsic momentum. Well, now we're going to have this intrinsic kinetic energy, and it is this property of intrinsic kinetic energy that lends itself to what I call the speed of light conjecture. If the velocity along the unobserved dimension where VU is equal to c times the square root of 2, so the speed of light, this sounds outrageous when you first hear it, but it makes sense. All the pieces of the puzzle fall together so nicely. So if our velocity along the unobserved dimension was c times the square root of 2, then the kinetic energy of an object would be the kinetic energy of any object. The square is 1/2 mv squared. You know, the kinetic energy of a car is, 1/2 times the mass times the velocity of the object squared. Any object. We would have the intrinsic energy of a mass. So E equals mc squared. So now when we substitute the VU for this term here, we end up with the energy is equal to E equals mc squared. So what Einstein calls the intrinsic energy of a rest mass becomes kinematically based. This is extremely simple derivation of E equals mc squared. It's just kinetic energy from us moving along an unobserved dimension. Anyways, now there are some variations on that, but I won't get into all that. So we have the property of inertia, and we also have, now it doesn't affect the relationship of special relativity because, well, it does. It determines a little bit the relationship of why is the speed of light a restrictive barrier, well, you can't go any faster than the opportunity to change can exist. So that's why I think it becomes increasingly more energy required to do so. But anyways, and here is more of an explanation about dealing with inertia. Any object we are in velocity along an unobserved dimension, any change in our direction induces the property of inertia. Now over here I describe a little bit about what makes photons move, and we have what's often described as the permittivity and permeability of electrostatic and electromagnetic fields in space. Well, these become functionally described as the permeability and permittivity and permeability become a characteristic based on the dynamics of interacting fields. So, and then what I propose in essence is simply, if I draw it as a two-dimensional relationship in a field, let's say this is the structure of observable space, and we are moving along this unobserved dimension, and there's a structure in observable space, and photons, let's say we started here, would be caught between the interface of the structure of one to another. So in essence, photons are becoming like sailboats with keels stuck within our expanding observable space, being expanded outward due to our interaction with the field of relationships of observable space. So rather than a permittivity, it's being a predicted field characteristic or byproduct of the interaction of two fields of space. Okay, we can skip that. And more, I'll skip that. Now, I also came up with the idea of why a photon has its wavelength longer in the past, and it's trying to work on the relationship of that cosmological redshift. And the thought occurred to me that it has to be somewhat correlated, or can be correlated to the velocity along the unobserved dimension. If the velocity along the unobserved dimension was faster in the past, the time period necessary to describe the wavelength would be longer in the past than it is in the present. So I'm beginning to impose this requirement that an imparted wavelength to a photon generated in the past would be longer. Now this presents some issues, but it's in essence what's happening is the cosmological redshift is being proportionally related or integrated to the velocity along the unobserved dimension. And okay, and then I talk about, well, it doesn't quite make sense. I was working on it. You can kind of see I'm working on it, but there's some things that didn't make sense in the model. Now, I take a break here.